Hello everyone. In this video, I'm going to talk about a Solidity programming language which we'll be using to write smart contracts on the Ethereum blockchain. Before starting, I'd like to quickly introduce myself. I'm Amrisha Bhagwati and I'm working as a software engineer at Kpro Solutions Private Limited. Kpro is a leading provider in data lake, cloud implementations, IoT, blockchain, analytics, machine learning, artificial intelligence, deep learning, and mobile application development. So without any further ado, let's get started with today's video. So the topics we'll be covering in this video are variable scoping, type conversion, which will include implicit and explicit conversion, block and transaction global variable, cryptographic global variable, address global variables, and finally contract global variables. So let us start with what is variable scoping. So variable scoping refers to the availability of a variable within a function or a contract. Solidity provides the following two locations for variable declaration, that is contract level and function level. So contract level global variables are also known as state variables, which are stored in the storage data location, and function level local variables are stored in the memory data location. So these function level local variables are available anywhere within the function and are not accessible from outside. The contract level global variables can be accessed by any function or modifier or a contract inheriting it based on the visibility specified. So we have three types of visibility specifier for the contract level global variables, that is public, internal, and private. So if the visibility is given as public, this means that the variables can be accessed by any function or a modifier within the contract or any other contract that inherits it. They are also directly accessible for external calls. And if the visibility specifier is given as internal, so it is same as public, but only with an additional constraint that it is not directly accessible for external calls. And if the specifier is given as private, again it is same as internal, only with another additional constraint that the contract, any other contract that inherits it, cannot access the variables. So this is all about variable scoping. Next, let us see type conversion. So type conversion refers to the conversions that require to copy a value into a variable of one type to another. There are two types of type conversions provided by Solidity. The first one is implicit conversion and the second one is explicit conversion. Now let us look at implicit conversion in detail. So in implicit type conversion, we do not need external help to perform the conversion, as this type of conversion is totally legal. Hence, there is no loss of data or any unmatched values. This type of conversion are type safe, that is error free. In Solidity, we cannot convert from we can convert from smaller to larger integral types. For example, we can convert uint16 to uint32 implicitly. So this is all about implicit conversion. Next, let us see explicit conversions. So we require explicit conversions when implicit conversions are not performed automatically by the compiler. Example of explicit conversion is converting uint16 to uint8. So if we want to convert from uint8 to uint16, it is converted implicitly. But if we want to convert from a larger integral type to a smaller integral type, we need to provide explicitly that we want to convert it. And in explicit conversions, data loss or unmatched values is possible. Now let us have a look at an example where I'll try to show you what this implicit and explicit conversion is. So in this contract, I'll try to show you how implicit and explicit conversions work. So in implicit conversion, I said that conversion can happen implicitly if the conversion is from a smaller to a larger integral type here, right? So here I have commented everything, so I'll show you how it works. So let me remove these comments. Okay, So in this, it's not showing any error. It's not giving us any error because implicit conversion is possible here. Because here we are trying to convert a smaller integral into a larger integral. So initially we have a variable x which was declared as a uint8 variable, and I have put the value or assigned the value as 10. So uint8 can hold the values from 0 to 255, and uint16 can hold the values from 0 to 2 to the power 16 minus 1, whatever that value will be. Okay, so obviously greater than 255. So here initially I'm putting the assigning 10 to this variable that is of type uint8, and then we are assigning x to a variable of type uint16. So here I'm trying to convert a smaller variable to a larger variable. So here this is possible implicitly. So here if I deploy this contract, here you can see x value is given as 10, y value is given as 10. So this is possible. Again, I'll just comment it to show you the next thing. So again, we can also write it, or perform the conversion explicitly. So here similarly I have assigned 10 to this x variable x of type uint8, and here I have explicitly converted x to the type uint16. Again, this will give us the same values, that is, I'll just deploy it once more, and here you can see x is 10, y is 10. Okay, so this is what implicit conversions and explicit conversion look like. So let us now look at this one. Now what's happening here? So here we are trying to convert a variable a of type uint16 to type uint8, right? Because here we are assigning a to this variable, and it's giving me error because we cannot implicitly convert a variable of larger integral type to a smaller integral type. So we need to convert it explicitly. So in order to convert it explicitly, I'll just write here uint8. Okay, and the error is gone. Okay, but one thing here is that uint16 can hold values 0 to the power n minus 1, which is greater than 255, and here I have provided 350, which is greater than 255, and here I'm explicitly converting this a to a variable of a smaller type. So uint8 cannot hold 350. So it will hold a value from 0 to 255. So it will give us some random or unmatched value. So if I just deploy it here, you will see A will give us 350, but B will return us 94, which is not a correct value. So I said that data loss or unmatched values might occur in explicit conversions. Okay, next let us see. So this is the same thing that I wrote, and I did it here itself. Here, now let us see this. Okay, so what are we trying to do here? So we are same thing, we are trying to convert a bigger integral value to variable to a smaller integral variable. So we'll have to give the we'll have to convert it explicitly. So uint8, and within brackets we'll have x, and I'll just remove this. Yeah, but here you see this uint16 can hold values from 0 to the power 16 minus 1. Okay, obviously 10 is within that range, and uint8 can hold the values from 0 to the power 8 minus 1, and even there 10 is within the range. So it will return us the correct value. So it will return us 10 itself. So I'll just deploy it once more. Here you can see x is giving us 10, even y is giving us 10. Okay, again this is the same thing. Now let us see this bytes. what do these bytes return? So here this is obviously giving us error because we are trying to convert a bigger byte type to a smaller byte type. Okay, so in order to, so we need to explicitly give it as, okay, bytes 1. Now let's see what does this return. So here byte 4 should return as this, and what byte 1 will return is that only the first byte, that is the first 2 digits, it will return. So let us just deploy it and see. Okay, I'll just cancel it. Sorry. Sorry, I did put the visibility as public, so no getter function was this was created. So I'll just cancel it once more and I'll deploy it once more. Okay, so here you can see byte 1 will return this. So byte 1 will return the first 2 bytes, that is 0, 1, 2, and byte 4 will return the entire thing, right? So first 2 represents first byte, 3, 4 represents second, 5, 6 represents third, and 7, 8 represents 4. Next, let us see. So this is the same thing that I had written, and here let us see what does this return. So we are trying to convert a smaller byte type to a largest byte type. Okay, so initially we had specified byte 1 is this 12 and byte 4, so we are explicitly converting it to byte 4. Okay, now let us see what does this return. Deploy. So byte 1 is returning same, and byte 4 here we can see we have 6 zeros padded here to make it byte 4. That is 12 is byte 1, 0, 0, 2, again 0, 0, 3, and the last 0, 0, 4. So this is all about the implicit and explicit conversions. Now let us talk about block and transaction global variables. So there are a few global variables that are not declared within the contract but are accessible from within the code. The ledger is maintained and accessed by the miners, and the contracts cannot access the ledger directly. Although some information about the current transaction and block is provided to the contracts in order to be utilized by them. Solidity provides both block and transaction related variables. Now let us have a look at an example of this block and transaction global variables. So this is an example where I'll try to show you what are the block and the transaction global variables are. So this is a contract definition where I have declared a few events here. That is the event followed by the identifier, and within the brackets we have the data type. Right? So here I have a few event, and from within this function from within this function invoking these events. So this block.coinbase refers to the miner's address. Then block.difficulty refers to the difficulty of that block. Then block.gas limit, it refers to the gas limit for the current block. Then gas left, so this refers to the amount of unused gas after the transaction happened. Then here transaction.gas price, it is the gas price caller is ready to pay for each gas unit. Block number refers to the block number. Timestamp refers to when that block was created. Now refers to the current time. Then message.data, it is the information about the function and its parameters that created the transaction. Message.sig, so it is the function identifier using first 4 bytes after hashing function signature. Message.value, it will give us any value. Here it will be sending any value. Then message.sender, it tells us about the from where the transaction was made. Then transaction.origin tells us about the first caller that invoked a contract. And this block hash, so it is the hash of the block containing the transaction. Now let me quickly deploy this contract and I'll show you what each of these will contain. So let me deploy the contract. Okay, so I'll just deploy it once more. Sorry, global variable, because I just cleared the console right now. So here we have this, right? So let me go to the log part. Yes, this is the log part. Okay, I'll just make it. Okay, so the first one is Coinbase, that is my address, right? So here we can have this is my address, and here we have the miners account. This is the miners account. Next we have difficulty, that is my event. Next here we have event my event, and this is the difficulty of this block. The next one is gas limit. It is again of type my event. This is my event, and this is the gas limit for this particular contract. Next is gas left, that is the unused gas. So again, this is my event. So here this is the unused gas. Next we have transaction.gas price, again my event. So here this is my event, and transaction.gas price is this, that is the caller is willing to pay, is here 1. Next is block number, which is of type again my event. So this is the block number. The next one is timestamp, that is the time when the block was created. And so this is the timestamp. Next again the current time. This. Then we have my bytes, that is the message.data. This is my bytes and this is the message.data. Then message.sig, again my byte 4. So this is the first 4 bytes. Then we have message.value. So we have sent just 0, so message.value should be 0. So here this is my event, and here this is the message value. Then we have message.sender. So here, where is it? My address. This is. So we sent it from this address, that the last one is 0C9B2. So here you can see it is 0C9B2. The next one is transaction origin. So here this is one my address, and again the same, from there itself the transaction originated, that is the first caller. And finally we have the block hash, which is this event my block, and this is the hash. Okay, so this is all about the block and the transaction global variables. Now let me go back to my slides. Now let us talk about cryptographic global variables. So Solidity provides cryptographic functions for hashing values within contract functions. There are 2 hashing functions, that is SHA-2 and SHA-3. SHA-3 function converts the input into a hash based on SHA-3 algorithm, and SHA-256 converts the input into a hash based on SHA-2 algorithm. And KCAC 256 is an alias of SHA-3 algorithm. Although in the current compiler version, SHA-3 has been deprecated, and instead of that we use KCAT 256. Now let us see an example of cryptographic global variables. So this is a simple example where I'll try to show you the cryptographic global variables. So this is a contract definition, and here we have a function that is returning two values of bytes 32, and here we are simply hashing this alphabet H using the SHA-256 algorithm, and again the same alphabet H using the KCAT 256 algorithm. Now let us see what it outputs when we deploy it. Okay, so here you can see this is the latest transaction that happened. So the coded output, so this is the hash of the alphabet H using the SHA-256 algorithm, and this is the hash for the same alphabet H using the KCAT 256 algorithm. So this is all about the cryptographic global variables. Now let me go back to my slides. Now let us talk about the address global variables. So both the contract and externally owned addresses have 5 functions and a single global variable. The single global variable is balance, which gives us the amount of ether on a particular account. And these are the 5 functions that the addresses gives us. So the first function sends the given amount of weight to an address and it throws on failure. The second function again sends the given amount of weight to the address but returns false on failure. The third function issues a low level call and it returns false on failure. The fourth function issues a low level call code and it returns false on failure. And this last one issues a low level delegate call and returns false on failure. So we'll talk more about these address functions in one of my upcoming videos. So for the time being, this is all about the address global variables. Next, let us see the contract global variables. So the first one is this. So this gives the current contract's type and can be converted to address explicitly. The second one is self-destruct. So this is an address recipient that destroys the current contract and sends it funding to a given address. And the third one is suicide. So this is an address recipient too, alias to self-destruct. Although in the current compiler version, this suicide has been deprecated and instead of suicide, we use self-destruct. So this is all about the contract global variables. Now let us have a quick recap of the topics that we have covered in this video. In the beginning, we talked about variable scoping. Then we talked about type conversion, which included implicit and explicit conversion. Then we talked about block and transaction global variables. Then we talked about cryptographic global variables, then address global variables, and finally we talked about the contract global variables. Thank you for watching this video. In the next video, that is Introduction to Solidity Part 7, the topics I'll be covering are solidity expressions, if-else, while loop, for loop, do-while loop, break statement, continuous statement, and finally the return statement. Kindly provide your valuable feedback in the comment section below and let us know of any topic you want us to make a video of or any issue you might be facing in your project. You may write to us at feedback@kpro.co.in. You can also subscribe to our channel if you want to learn more about technologies like cloud, data science, ETL, data lake, DevOps, big data testing, cloud testing, etc. And you can also follow us on YouTube, Facebook, LinkedIn, Twitter. Thank you very much. Let's keep learning.